Welcome to Chapter 7, our first look at inference. There's two forms of inference. This chapter will be talking about hypothesis testing. Hypothesis testing is about making a decision about a parameter, that is, making a claim about a population based on a sample. Now, that may sound like the only way you can make decisions. You've got the limited information available to you, and you use that information to make a general claim about a population. In statistics, we look at this from the point of view of how much variation could be in that sample. So we might ask if the statement is true or not. However, because we're dealing with samples, we need to remember that our statements are about random experiments. So instead we ask how likely the statement is. Confidence intervals are asking you for an estimate of a parameter, that is, another statement about a population, again based on a statistic from a sample. And we might say, what is the value of the parameter? However, again, because we're dealing with samples, our statements are about random experiments. So instead we ask, how likely is a range of values? So our first discussion is, what is a hypothesis test? So a hypothesis is an educated guess about a parameter. Intuitively, we may say, let's go out and look for evidence to support our hypothesis. But remember, we don't know if our hypothesis is true or false to begin with. And if we're simply sorting through evidence for that data that supports what we claim, we're not doing statistics. So the way that really works is we have to begin by assuming that our idea is not true. Now, at first, that may seem counterintuitive. It's not what we're trying to do. But it allows us to assume something. We can begin with the assumption that our idea is not true. We can say that that is our assumption. We then gather evidence, and if that evidence would be very unlikely, assuming our idea is not true, then it is more likely that our idea is true. So we work backwards. In a sense, we use what we're trying not to show against it. So let's look at an example. The life of a battery. Now, who knows what this battery is? It could be the battery in a pacemaker, in which case it's very important. It could be the battery in your calculator, in which case it's probably not as important. So without knowing the context of this battery, without knowing how important a failure of this battery is, let's talk about a hypothesis test. The manufacturer of the battery claims that the mean life is 500 days with a standard deviation of 25 days. That's their claim. We don't think that the batteries last that long. If we can support our view, if we can support our claim that the batteries don't last that long, then maybe we can get out of the contract with this manufacturer. The random variable x is the life of a single battery. The parameter mu is the mean life of all of these batteries. We're going to pick a sample. We're going to use a random sample to avoid bias. We should probably choose 30 according to the central limit theorem. So let's start by looking at our data. So this is for the 30 batteries that we collected, how long they lasted in days. So that first battery lasted 491 days, and it looks like the last one 486. Some are longer, some are shorter. Notice that some of these are over 500 days. There's a 502, a 504, a 501, a 503. Some are shorter, some are longer. If you average these 30 lengths in days, you get 490 days. Now that looks promising for our claim, but it could just be a coincidence. Maybe we just happened to pick a lot of short-lived batteries. Now remember, we're going to use the distribution of the sample means, the distribution of the sample, to determine whether this really would happen, what the probability of this happening, or something more extreme, if we assume the null hypothesis. So let's talk about those. There are two hypotheses. The null hypothesis is the historical value, the claim of the manufacturer, or the product specification. These are just a few examples, but they give you an idea that this is what we are making an alternative hypothesis against. So the null hypothesis is the claim of the manufacturer, of the government, of some corporation. We want to prove that the alternative hypothesis is true. That is the negation of the null hypothesis. So this is what you want to accept as true if you reject the null hypothesis. So there are two symbols that are commonly used for the alternative hypothesis, H sub A or H sub 1. We'll use H sub A. The null hypothesis is H sub 0. Null is, of course, 0. So we're going to start by setting up the expressions for these two. The null hypothesis is that the population mean is equal to some particular value, mu sub 0. Now, our alternative hypothesis could be one of several things. Either the true population mean is less than that value, the true population mean is simply not equal to that value, or the true population mean is greater than that value. Mu sub 0 represents the value that the claim, that is the null hypothesis, says that the population mean is actually equal to. So a hypothesis is just a sentence with a name. So the name of this sentence is H sub 0, the null hypothesis. The subject is the population mean mu. The verb is equals, and that's equal to the object mu sub 0, that claimed value. Now let's convince ourselves that simply having an average less than 500 doesn't really tell us what you'd think it tells us. In other words, we need to know how many standard deviations away it is, what the probability of that being true is. So for example, notice that we're in a kind of gray area here. If our sample mean was 235 days, it would be a slam dunk. There is no way with the standard deviation that they claim that it could be 235 days. Remember, we're allowed to assume the null hypothesis. And in the null hypothesis, we were told that the standard deviation was 25 days. So this is like 5-6 standard deviations away. That would be a slam dunk if our population mean was 235. If it was 435, we'd say, yeah, probably. That's more than 2 standard deviations. It's about 2.5 standard deviations away. Remember, we're counting in 25s from 500. So we'd say, yeah, that's probably enough evidence to support our claim. If our sample mean was 483 or 498, we'd have to conclude, well, maybe that's just chance. So you can see where this is going. We want to know where that boundary is. We want to be able to find it. So let's remind ourselves of sampling distributions. If the mean really was 500, as the null hypothesis, as the manufacturer claims, what different sample means would we get if we did repeated random samples of 30 batteries? Sometimes we'd get more, and sometimes we'd get less. But let's remind ourselves of the shape, the center, and the spread. The shape of our distribution would be normal. That's because the sample is at least 30. The center of our sample means would be the mean of the sample means, and that's the same as the population mean, 500. The spread, or the standard deviation of our samples, would be the standard deviation of the sample means, and that is shown, as you remember from previously, as sigma sub x bar, and that is by definition the population standard deviation sigma divided by the square root of n. So earlier I was saying that the standard deviation for a single battery is 25 days. But the standard deviation of the sample means is only 4.56 days. And that's because, remember, we're dividing it by the square root of n, and in this example, n was 30. So let's look at this distribution. So here is a normal curve with a mean at 500 and a standard deviation of about 4.5 days. And we had a sample mean of 490. And so we asked the question, what's the probability of getting a mean of a sample of 30 that is at least as extreme as 490? So that's the area shaded to the left away from the mean from 490. Let's put this in more formal terms, and the best way to do that is with the z-score. Remember that the z-score counts standard deviations. It tells us how far a data point is from the mean. So notice in the denominator, when we're counting in standard deviations, we're actually counting in the standard deviation of the sample means. So that's the population standard deviation sigma divided by the square root of n. And the numerator is just how far mu sub 0 is from the mean. So when we go through and we do this arithmetic, we learn that our sample mean is negative 2.19 days away from the population mean. Remember, we're allowed to assume that the null hypothesis is correct. So that gives us a population standard deviation and a population mean. Our sample mean of 490 is actually negative 2, that is 2 standard deviations to the left. Now the question is, what is the probability of being 2 standard deviations to the left or more extreme? And the probability is about 1.42%. So all of a sudden we can see that if the manufacturer's claims are true about the population mean and the population standard deviation, then our sample of 30 would have a mean of 490 or more extreme, that is fewer days, 1.42% of the time. Okay, so let's formalize these. The test statistic is our z-value, so that's exactly what you'd expect. The only new part here is, remember that our standard deviation is the standard deviation of the sample means, so we have to take sigma and divide it by the square root of n. Then there's a p-value, and this is new. The p-value is a probability that the test statistic will take on more extreme values than the observed statistic, given that the null hypothesis is true. So we're allowed to assume that the null hypothesis is true. That gives us a lot of information that the manufacturer or that the government claims is true. We then compare that and we ask, what would the probability be that that test statistic will take on more extreme values than the observed statistic? So the observed statistic here is that x bar is 490 days. We're assuming that the null hypothesis is true. That's where we got sigma, and that's where we got mu sub 0. Now, we need to talk about errors, and this is when we need to make a decision about where that boundary is, not in terms of numbers of days for the battery's life, but in terms of probabilities. So notice that there are 2 kinds of errors. We can reject the null hypothesis when it is true, or we can fail to reject the null hypothesis when it is false. Now, the other 2 cases are fine. If I fail to reject the null hypothesis and it's true, there's no error. If I reject the null hypothesis and it's false, there's no error. So there's only these 2 errors. So a type 1 error is rejecting the null hypothesis when the null hypothesis is true. And a type 2 error is failing to reject the null hypothesis when the null hypothesis is false. Now we're going to assign probabilities to each of these. So we're going to call alpha the probability of a type 1 error. And remember that a type 1 error is rejecting the null hypothesis when in fact the null hypothesis is true. So just a quick reminder of the way we write probabilities. If I write h sub 0, I'm saying that it's true. Notice that later on, when we're talking about the probability of a type 2 error, we'll put a tilde in front of the h sub 0 to say that the null hypothesis is false. So in this first case, alpha, just to summarize, is the probability of a type 1 error. That is the probability that we reject the null hypothesis given that it's true. Alpha is called the level of significance, and we design our test to use alpha as that threshold to decide when we either reject or fail to reject the null hypothesis. For a certain sample size n, if alpha increases, beta decreases. And for a certain level of significance alpha, if n increases, that is, our sample gets bigger, then beta decreases. Now, how do you find alpha and beta? Generally, we choose alpha. There are only 3 values that are usually picked for alpha: 1%, 5%, or 10%. Beta is very difficult to find, so usually it is not found. In fact, I will not be asking you to find beta. If you want to make sure that beta is small, you take a sample as large as you can afford, assuming that it is a representative sample. So that's one use of power. You want beta to be small, so then the power of the test is large. Now, we're going to talk about type 1 and type 2 errors and the level of significance alpha in the context of a crime. If someone is brought to trial and the crime is very serious, then the idea is that the probability of sending them to jail when they're innocent needs to be very low. So if a type 1 error is really bad, then you pick alpha of 1%. Whereas if a type 2 error is really bad, then you pick an alpha level of 10%. And if they're equally bad or neither is bad, then you go down the middle and choose 5%. The main thing is always to pick alpha before you collect the data and start the test. In other words, you don't know where z is going to end up being. You don't know what that probability of being at least as extreme as your sample is going to be before you choose alpha. So let's talk about this in the context of our batteries. Let's say that this is a battery that powers the pacemaker in a person's heart. In that case, if the null hypothesis is false, that is, if the manufacturer's batteries don't last as long as they claim, but we fail to reject that claim, in other words, our analysis says, nope, the batteries are fine, no need for concern, then we're basically putting someone's life at risk. So in this case, if the batteries are for a very important application and their failure is very bad, then we'd say that we wanted to represent with our choice of alpha that a type 2 error is bad. So we're going to choose 10% for our alpha, assuming that these batteries are really important. Okay, so let's do everything in one place. Let's wrap up this discussion of batteries. We'll start by stating the random variable and the parameter in words. So let x be the life of a battery. Let mu be the mean life of all batteries. That's a population parameter. Then let's state the null and alternative hypothesis, and of course that level of significance. So the null hypothesis is the manufacturer's claim that their batteries last 500 days. Our alternative hypothesis is that they don't last that long, that the population mean is actually less than 500 days. And because these are important batteries, we've chosen alpha to be 10%. So now let's go through and do the assumptions for this test. So every hypothesis has some assumptions that have to be met to make sure that the results of the hypothesis are valid. Now, this is terribly important. It's easy to do the arithmetic, to perform the test, to make a claim, but you have to ensure that the necessary prerequisites of that test are met. Another thing to say, this is the first of several kinds of hypothesis tests we're going to talk about this semester, and the assumptions are different for each test. So this test has the following assumptions. So first off, a random sample of size n is taken. So you do need to check that in some way or other, a random sample of a fixed size is made. Now, that random sample could also be equally good if it was a representative sample, but we'll look for a simple random sample of size n. Now, this did occur in this example since it was stated that a random sample of 30 batteries were taken. The population standard deviation is known. Now, remember, this came to us from the manufacturer, so we are using the null hypothesis. Again, this was true. We were given that the standard deviation of all batteries was 25 days. And then this third requirement, the sample size is at least 30, or the population of the random variable is already normally distributed. And because the sample size was 30, that condition is met. In other words, we're considering probabilities coming from bell curves, from normal distributions. So we really do need to ensure that that last condition is met. Now we're asked to find the sample statistic, the test statistic, and perhaps most important of all, the p-value. The sample statistic came from our 30 batteries. They had a mean life of 490 days. The test statistic is z. That's counting in standard deviations of the sample mean, how far our sample statistic is from the population mean claimed by the manufacturer. So in the numerator, we're saying, well, it was 10 days apart, but we're counting those 10 days in standard deviations of the sample mean. And of course, that means that we have to take the population standard deviation and divide it by the square root of n. That gave us our z-score of negative 2.19. The negative means that we're to the left. So let's use our calculator to compute that p-value. So to do that, we're going to launch Bell. So I'm going to press Program. Bell is the first choice. So I'm going to press Enter. Enter again to launch it. We're interested in finding a probability. So that means we answer 0 to that first question. We have a normal curve. N is at least 30. So we're going to enter 0 for that second choice. We've got the mean and the standard deviation. That is, we've got x values. So I'm going to enter 0 for the next question. The mean, according to the manufacturer, is 500. The standard deviation, I could compute this earlier, or I can actually have my calculator compute it as I enter it. So the population standard deviation was 25. To make that into the standard deviation of the sample means, I need to take that population standard deviation and divide it by the square root of n. Then it says, what area do we want? Well, we're to the left of the mean, so we want values that are at least as extreme as that. So even further to the left, so that'll mean that we enter 0 for that next one. And of course, now what was our x value? To the left of what? To the left of our sample mean of 490. And it computes the p-value, the probability that the mean would be 490 given the null hypothesis as about 1.42%. You can compute the mean or the standard deviation of the sample means ahead of time, or as you just saw, you can enter that into your calculator as an expression. And again, that gives us that the mean of the sample means is 4.56. This last expression says that the probability of getting a value of 490 or more extreme, given the null hypothesis, is only 1.42%. Now, we're not done. We still have 2 more steps. We have to have our conclusion in statistical terms and our interpretation in English terms. So our p-value is less than alpha, since 1.42% is less than 10%. So this is below our threshold of weirdness. So we would accept anything up to 10%. But we've got something far lower than 10%. Our sample, or something as extreme as it, only happens 1.42% of the time. We were prepared to accept something happening up to 10% of the time. But because of that, we're going to reject the null hypothesis. The battery life with a probability of 1.42% was less than 500 days. So in general, you reject the null hypothesis if the p-value is less than alpha, and you fail to reject the null hypothesis if the p-value is greater than or equal to alpha. The interpretation is when we state our results in words. So here we reject the null hypothesis and tentatively accept the alternative hypothesis. That is, we tentatively state that the batteries last less than 500 days. This is statistically significant. Okay, let's summarize by going over this process again. So the first step is to state the random variable and the parameter in words, so you know what it is that you're talking about. Then state the null and alternative hypotheses and the level of significance, that alpha that you've chosen. Then state and check the assumptions of the hypothesis test. Then find the sample statistic from the data that you collected, the test statistic using the null hypothesis, and then using Bell, compute the p-value. P stands for the probability. Then in the fifth and sixth step, we make our conclusion and interpretation. When we make our conclusion, we either reject the null hypothesis in favor of the alternative, or we fail to reject the null hypothesis, in which case we say there's not enough evidence to support the alternative hypothesis. We never accept the null hypothesis. Remember, our test was designed to make claims about the alternative hypothesis. And that ends 7.1, our first and tremendously important introduction to hypothesis testing.